Hi, class. This is Mr. Hart. In this podcast, I want to go over the things we covered in the first week of our new unit on forces. There is quite a bit we need to cover, so I'm going to try and do my best to keep the video as short as possible, but again, we still need to cover quite a bit of material. So let's see how we do. But first of all, let's talk about forces. Okay, what is a force? What do you think of when we think about a force? And a lot of people think of like pushing something, or Star Wars use the force, or something of that nature. But if we're looking really at the physics definition of a force, it's any type of influence that can change the motion of an object. Okay, so in the purest definition of force is the influence which tends to change the motion of an object. Okay, it doesn't always. You can still apply a force but not change the motion, but usually it will. Okay, so forces have value and direction. Okay, so they're a vector quantity, if you know what that means. Okay, but you have a specific direction you push and a specific value of the force, or how much you're pushing, right? And then forces are measured in newtons, and we'll get to this a little bit later on, but this is a unit to help us measure force. Okay, so if we look at an example in daily life, if someone is pushing some groceries, there's a lot of forces that are involved. Okay, there's the force of gravity on the person. Okay, there's a force of gravity on the cart. There's the force of the floor pushing up on the guy's feet. There's the force he's putting on the floor to push back to help him walk. Okay, the cart has friction on the wheels. Okay, that's a force. He's pushing on the cart forward, so that's a force. Okay, and I apologize, my arrows aren't the straightest, but the point is there's a lot of forces happening, right? Just all over the place. And in a lot of scenarios, we can't model every single force. Okay, so what we need to do is we need to find a good way to show what's happening without making the drawings too confusing or too messy. And so we use what's called net force, which is the force or the total force acting in each direction. So how much force is pushing up, how much force is pushing left, how much force is pushing down, and how much force is pushing right. Okay, so we add up all the forces and make one net force in that direction. Okay, and if an object has forces that are equal in both directions, okay, then that is called equilibrium. Equilibrium is if the net force is zero in all directions. Okay, so let's look at an example of someone pulling on a rope in a tug of war, right? There's lots of forces happening, right? This person's pulling this way. Okay, this person's pulling this way. These two are pulling the other way. Okay, the rope has a little bit of tension, is what it's called, that wants to pull back in. Okay, there's forces on the ground and everything, but we can basically use a summary of all these forces and make a net force. Okay, and just say there's this much force going this way, and there's this much force going that way. Okay, so if these two forces are the same, then the rope is in equilibrium, so it's not going to move or change direction. Okay, so we take a very complex diagram and make it into a simpler one with just two arrows using net force. Okay, all right, so what types of things can a force do? Okay, it can make something speed up, right? Someone kicking a soccer ball puts a force on the soccer ball, making it speed up very dramatically. It can make something slow down. Okay, think about brakes on like a semi-truck or a car. Okay, those brakes are helping the car slow down. You can make something change direction, okay, like a tackle in football. It can make something rotate, like on a wrench, or it can make something change shape. Okay, as you compress it or uncompress it, you can change shape. So for this class, we won't really worry about these two down here, but we'll mostly focus on these three: speeding up, slowing down, and changing direction. Okay. So in order to figure out if something's going to speed up, slow down, or change direction, we really need what's called a free body diagram, or basically a diagram showing all the forces acting in each direction, or the net forces, as we were discussing. So, for example, this little box here on this ramp has the force of its gravity, the weight, it has the force pushing up from the floor, it has the force of friction. Okay, so these three arrows show what all those forces are going to be. Okay, so we can do this for any object. Okay, and we usually do it really simple, you should draw a square or a dot or something, okay, to draw or to start from. So instead of using this whole car and focusing on where the forces are on this car, okay, we'll just use one dot and say all the forces start from here. Okay, that's not really a good physical understanding, but it does help us do the math easier, and it's a simplification we can make without losing too much information. Okay, so let's pretend this car is just driving down the road. It has the gas pedal on. It's going about a constant speed down the road. Okay, there's a force going down, which we call the force of gravity, right? Gravity is pulling on the car. We have the force going up, which is the car or the floor pushing up on the car, right? We call that Fn. We'll talk about that in a second, but there's that force pushing up, force pushing down, right? These two are going to be the same because otherwise the car would be either plowing into the ground or flying up into the sky. Neither of those are happening, so we know that these are in equilibrium. Okay. Then we also have the force of the car engine, or the force applied, you could say. The force of the car engine pushing the car forward. And we also have the force of friction. Hopefully you can read that. Force of friction pushing the car back. Okay. So if we take the car out of this picture, okay, this is our force diagram. Okay. The force of gravity pushing down, the force of the floor pushing up, the force of the engine pushing it forward, and the force of friction pushing it back. Okay? So we can make this simple diagram for any type of object, any type of force. Okay? So we do this for a bunch of different scenarios, so you hopefully can get a good idea of what's happening, what forces are being applied. Okay? All right, so we also watched this video about how much force you would need to lift yourself in the air by using just simple hydrogen balloons and things like that. Okay, so that's an interesting video if you want to watch it. Okay, and then we talked about Newton's 3 laws. So Isaac Newton was the first one to really model force. Okay, he came up with 3 laws to help us describe what forces should be doing, how they interact, and really what the mathematical basis is for them. Okay, so Newton's first law is that any object at rest will stay at rest unless a force acts upon it. Okay, so any object at rest will stay at rest unless a force acts upon it. So forces is what makes something move initially, right? So if I don't have any force on something, it's just going to sit there. Okay, but I also have, but we also have the other version of this. So any object moving will continue moving unless a force acts upon it. Okay, so if something's just moving down the road, okay, it's not going to slow down unless there's friction, right? There's got to be some force. So otherwise, it just keep going. So if you're in space and you're moving, if there's no force, you're just going to keep moving. Okay, so this is called inertia. This idea that objects don't want to change their motion unless some type of force is pushing on them. Okay, Newton's second law was the force, or is really the mathematical equation that force equals mass times acceleration. Okay, so you should know this equation, and it's really the basis for a lot of other equations, but it's just a simple idea that as I apply a force, that I'm going to cause an acceleration. Okay, so the more force I have, the more acceleration. Okay, this also explains a lot of things that we see in daily life, like we put a force on the earth, okay, from gravity, and it puts a force on us. But the problem is it weighs a lot more than we do, right? The mass of the earth is much larger than we are, so the force is the same, but the mass is much larger, so the acceleration is going to be very, very small. Okay, so hopefully you'll be able to apply this and see how it works for a lot of situations. Okay, another way to think about it is if I'm pushing a large object, like a big concrete block that has a lot of mass, okay, or if I'm pushing a very small brick or something that's very small, very low mass, okay, they're going to accelerate at different rates because even if I'm putting the same force, the mass is going to be different, causing different accelerations. Okay, so hopefully you can see different applications of that and get some practice with that. But then the last law is Newton's third law, which is every action has an opposite and equal reaction. Okay, so if I apply the force on one object, that object's going to apply the same force back. Okay, so if I push down on the floor is going to push up on me. Okay, the force that 1 pushes on 2 is the same as 2 pushes on 1. Okay, so you can't have a force by itself. It always comes in pairs in an opposite and equal direction. Okay? All right, let's keep going. We can get through this. Okay, if we look at the units of force really quickly, the units of mass is kilograms. The units of acceleration is meters per second squared. So we get kilograms meters per second squared. This is what we call a Newton. Okay, so this unit right here, kilogram meters per second squared, the unit of force, is what we call a Newton. Okay, so that's the unit of force. Okay. All right, if you're doing participation, try this example problem really quick. A car receives a force of 20 newtons. If the car has a mass of 400 kilograms, what is the acceleration of the car? Okay. All right, and then the last thing we want to talk about is the idea of weight. Okay, so you probably have heard weight and mass interchangeably, but they're kind of slightly different ideas. Okay, so weight is the force an object gives because of the pull of gravity. Okay, and so an object wouldn't have weight if there was no gravity. If there wasn't any force, we couldn't have weight. So the force or weight that we have is equal to our mass times our gravitational acceleration. So if you think of the F equals ma equation, you can see that this is just a simple replacement of g with a. Okay, so the force or weight is equal to the mass times g. Okay, the force we give because of the pull of gravity. Okay, so if you're doing this for participation, please answer this question. An object has a mass of 50 kilograms. What is its weight in newtons? Okay, so you're just going to use that same equation we just looked at. Also try this one. An object has a mass of 12 kilograms. What is its weight in newtons? Okay. All right, and the last thing we talked about is how do we measure force? How do we measure weight? And so we looked at some of the different methods that have been used historically. So probably the very first thing that was ever used was a balance. Okay, a balance is a type of scale to help us measure weight. We've also learned how to use a triple beam balance, which uses these different distances to help balance it out and determine the weight. And we've also used spring scales. Isaac Newton actually invented these. They're called Newton spring scales because a spring has a determined distance it goes when you stretch it. The amount of force that you need to apply is set. So Isaac Newton figured out a way to calculate how much a spring is going to stretch, and so you could determine how much force is being applied, how much weight there is. Okay? So then we did the measuring weight labs, and you got to use all these different types of scales, and that is all we covered for week 1. So hopefully that wasn't too long. Let me know if you have any questions, and thank you for watching.